So the last half of 19.4. So 19.4, this is going to be part 2. And we're going to look at different cells here. We're going to look at electrolytic cells. So in our voltaic cells or galvanic cells, what we are doing is the chemical reaction itself was producing the charge. It was producing the current that we would measure. Now in an electrolytic cell, what we're doing is we're taking a battery, we're taking a charge source, and we're putting it into a substance. So in this example, we can start with it. We have molten sodium chloride. So we have sodium chloride at really high temperatures, we're melting it down. Well, if we're melting it down at really high temperatures, we're going to have sodium ions, and we're going to have chlorine ions floating around. Again, molten sodium chloride is probably not something you're going to do in a lab, reach those types of temperatures. It's more of a thought experiment. Okay, so we have it hooked up to a battery. Anytime you see a battery like this, you always want to know that wherever this shorter line is, that is what the electrons are flowing away from. So they're always going to flow in this direction. So away from the shorter line. So that's the symbol we use for a battery. So the electrons are flowing down into what's called a cathode. So this is cathode because, again, the cations are being attracted to it. It's the cathode. The one difference here in electrolytic cells is this is going to be labeled the negative terminal, though, where in our voltaic cells that would be labeled the positive terminal. Is now our negative terminal. It's not a lot of fun that way. Anyway, here we're pulling electrons away. Well, if we're pulling electrons away, what's going to happen is we're actually going to pull them away from the chlorine that's there, and we're going to form chlorine gas. So chlorine is going to be evolved at the anode, and we're going to make sodium metal at the cathode, and it will actually it'll come together, and it will probably actually fall out on the bottom there. We'll get some sodium metal on the bottom. Now, obviously, kind of a dangerous thing to do. We're making sodium metal, and we know that's very reactive as it goes. So what other things? What would happen then if we take that sodium chloride and we throw it in some water instead? Because that's going to be a lot easier than going through and melting sodium chloride. That's going to take really high temperatures. Well, if we take sodium chloride, we're putting it in water now, and now again we have our battery. Notice the short side, we have electrons running away. So, and we have it running through an inert electrode, so the electrode may be made out of carbon or platinum. Sorry about the bell. A lot of times platinum, ideally. Sometimes it's a carbon electrode. So the electrons are running down. This is our cathode. Again, it has a negative charge. It's going to attract the positive ions. Over here, with electrons being pulled away, it's going to be a positive charge. It's going to attract the negative ions. Well, notice on this side what's going to happen is still we have the chlorine molecules coming here, losing their electrons, which flow through the circuit. Notice what we have. We're making chlorine gas, just like we did before. However, let's look at what happens at the cathode side. At the cathode side, we're not making sodium, okay? We're not going to make sodium metal. And that's probably a good thing because sodium metal is very reactive with water. So what we are doing instead is, notice this is aqueous sodium chloride, so it's sodium ions, it's chlorine ions, but it's also dissolved in water. So in this instance, what's happening is the water is actually reacting. At the cathode, it is the hydrogen gas that is being pulled away from the water, leaving hydroxide behind, and the hydrogen molecules are coming together and making hydrogen gas right up here. So if we have that sodium chloride dissolved in water, the hydrogen gas is going to be evolved instead of the sodium, and we're going to be left with sodium ions and hydroxide ions. Okay, so why is that? Well, it has to do with the reactivity. So we could look at a standard electrode potential table, or we could just look at a reactivity table, and this is going to be easier for a comparison. Notice where hydrogen is. Notice where sodium is. So sodium is more reactive. When things are more reactive for metals like this, remember what that means is they want to stay in solution. So the sodium is going to stay in solution preferentially to the hydrogen. So because it's dissolved in water, now the hydrogen will evolve from the water before the sodium does. Now notice most of the metals, if we have a lot of metal salts, most of those metals are going to stay in solution if we electrolyze them, and we're actually going to make hydrogen gas instead. Notice it's only the ones that are fairly non-reactive that will plate in preference to hydrogen. So that's one thing we want to be aware of if we ever have problems where we have an aqueous metal salt. If it's in water, we have to be aware that that hydrogen gas might be produced instead of the metal. Now notice we actually have 3 products of this. If we run this long enough, we're going to make chlorine gas, we're going to make hydrogen gas, and notice what's left over, sodium hydroxide. We're going to make hydroxide over at the cathode here. We're going to have sodium ions left, so we'll make sodium hydroxide. So it's actually an industrial process to make sodium hydroxide, chlorine, and hydrogen. Going on, other things we can do a lot with electrolysis. Important one we can do is plating. So when we plate, here's what we're doing. Again, we're hooking up a battery. Now notice we have electrons flowing through in this direction. So we have our electrons flowing. Because this is electrolytic cell, this is our negative terminal. This is, by the way, our cathode. Over here it's positive. This is our anode. And notice what we have. We have a spoon. Could just be a spoon from the cafeteria. And over here we have a chunk of silver. Well, what's going to happen in this? Well, in this type of circuit, and notice it does have to be dissolved in the same metal salt. It's dissolved in, or I shouldn't say dissolved, but it's in a solution of silver nitrate. So what's going to happen is that negative terminal is going to attract the silver ions, right? And they're going to plate here. They're going to pick up electrons. They're going to plate here. They're going to be reduced at the cathode, and here they're going to be oxidized and they're going to go into solution. So we have the same metal ion moving across in this electrolytic cell, and this is our plating process. So it's a process we can take this spoon, make it our cathode, and we can plate our silver on it. Because the electrons are running down, the silver ions are going to pick up those electrons. They're going to be reduced, and they're going to form a nice metal coating around that. Now this isn't the best picture. This might be a better picture of it. So notice again what's happening. We have a piece of silver. We have it hooked up to a battery. We have the flow going through on this side. This is our cathode, our negative terminal. It's going to attract the silver ions. The silver ions are going to leave our metal strip here. So at one side, at the anode now in plating, this is kind of what's different about when we do plating, is it's the same metal that's being oxidized and reduced. So at the cathode, notice it is being reduced. It's accepting the electrons. On the anode side, it is being oxidized. It is going into solution. And here's just a picture of me as a younger man working in the electrolysis plant, coating some things, cups, stuff in silver. I don't know what those are cigarette holders, I guess. Anyway, so examples of electrolytic cells. Okay, and why would we plate things? Well, we plate things because this metal might be less reactive. We can coat maybe a more reactive metal that might corrode more easily. We can coat it in a less reactive metal and thereby kind of preserve it, make it last a little bit longer. Or it might just be prettier. We might do it for pretty. A couple other pictures of electrolytic cells. Notice here we just have the electrolysis of water itself. If we electrolyze water at our anode, we'll get our negative ions, our oxygen ions coming together make oxygen gas. At our cathode, we'll have our positive ions, our hydrogen ions coming together make hydrogen gas. Okay, that's the electrolysis of water. Notice we have the electrolysis of copper chloride. So this is copper electroplating. So we have copper chloride in solution. So there's water here, but notice the difference between the sodium chloride example. In this example, we have the chlorine ions still making chlorine gas at our anode. That's the same thing we had in our sodium chloride. But notice in this one, we're not making hydrogen gas. We will actually plate with our copper. And again, why we plate with our copper in that example is because copper, again, is less reactive than the hydrogen. So copper will come out of the solution and plate preferentially to the hydrogen. Now notice we can't plate with these other metals in an aqueous solution because they're more reactive than hydrogen. They will stay in the solution, and instead of plating, we'll be making hydrogen gas. A couple things we want to remember about the difference between electrolytic cells and our voltaic cells before we leave this topic is if we look at them side by side, a couple things we want to notice. Remember, voltaic cells, it is the chemical reaction that's producing the electricity, I guess. Notice right here, the chemical energy being turned into electrical energy. And again, that has to do with the difference between the reactivities of the metals that are in it. So notice in this one, there's a copper sulfate solution. Maybe on this one we could have, again, the more reactive metal is always going to be the anode, perhaps zinc, perhaps copper over here at our cathode. Notice our cathode is labeled positive because our positive ions are moving there, becoming reduced. And over here we'd have the zinc going into solution, becoming oxidized at our anode. And again, that's a negative terminal in a voltaic cell. If we switch over to the other side, now in the electrolytic cell, we're providing the current. We hook it up to a battery. The electron flow is going to come from that battery from the short terminal there. So now our cathode is labeled negative instead of positive over here. It's still going to track the cations, though. So if we have copper sulfate solution here, it's going to track the copper sulfate. It's going to form copper. Over on this side, say we had a piece of copper itself, that copper would go into solution on the other side, and it'd be oxidized at the anode. So nice little summary of these things. We can just go down the list here. So notice, again, voltaic cell, the chemical energies become electrical. In our electrolytic cell, we're providing the energy, the electric energy to make a chemical reaction, essentially. The electrical current results in the chemical reaction here. The chemical reaction produces the current. That we already know. Here's the big difference that's highlighted here in yellow is the cathode and anode. The cathode now is always, the cations always move to the cathode. That's how you can always label the cathode no matter what type of cell you're using. However, in a voltaic cell, it's labeled the positive terminal because, again, it's the chemical reaction producing the energy, so we label it based on those positive ions moving there. Here, it's the electrical energy producing the chemical reaction. Because electrons are flowing in down it, we call that the negative terminal. Now, the flow of electrons here goes from the positive electrode to the negative electrode. In an electrolytic cell, the electron flows from the negative electrode to the positive electrode here in the voltaic cell. So what we can always remember is always the electrons, no matter what, are always flowing towards the cathode, away from the anode and towards the cathode. That really doesn't change. It is really just what we label the negative and the positive terminal is what flops in our electrolytic and voltaic cells.